we're doing good. Let's see what we're looking at this week. Like I say, we're going to get into the fundamental theorem of algebra, which you think you'd learn on week 1 of Algebra 1, but and some other good theorems. We're getting some good stuff for math because we're getting into some theorems that have been developed over the years and proven. They're proven, so they're theorems now. And you get into some real interesting stuff when you get into these kind of things in math. It's more college level thinking sometimes when we get into some of this, which is a lot of fun getting into those type of things. So let's look at our grade screen and see where we're supposed to be at. Oh, I don't have a 100. What did I miss? Oh, I've got an 80%. I got to redo my long division. Ah, man. Let's see. We're on the theorems of algebra and the rational root theorem and Descartes' rule of signs. Man, there's some cool stuff this week. Descartes' rule of signs is so neat. Rational root theorem. We got a lot to cover. We got to get into it here. Theorems of algebra lesson. We'll see how this runs. I think we can get through it all. All right, so most people, even if they're not mathematically minded, have heard of the Pythagorean theorem. You ask people about math, they may not be able to remember what it is, but they can tell you, oh, Pythagorean theorem, yeah. Well, that states that the sum of the squares of two sides of a right triangle is equal to the square of the hypotenuse, or what you probably remember is a squared plus b squared equals c squared. But what is a theorem? A theorem is a statement. Doesn't have to be mathematical in nature, but it's a statement proven by experimentation. And it's time to discover 3 very important theorems that are going to help you work with polynomials. So that's what we're doing today. We're going to learn what key features of a polynomial can be found using the fundamental theorem of algebra and the factor theorem. And how does the remainder theorem allow for zeros of a polynomial to be identified? So since we know how to do synthetic division and good stuff, we're going to use a lot of that. So let's talk about the fundamental theorem of algebra. The solutions to quadratic equations, which we worked with those a lot through math, especially in high school, can be found by applying the quadratic formula, by completing the square, and sometimes by factoring or graphing. If the value of the discriminant, b squared minus 4ac, if you remember that, that's part of the quadratic formula. If the value is a perfect square, then you can factor it. Like x squared plus 11x plus 18 equals 0 can be factored since the discriminant equals 49. If you take b squared, which is the 11, and you subtract 4 times a, which is just a 1, and c, which is 18, it'll end up as 49. Okay. So that tells you that there are 2 real factors that are integers. And then when we graph it, we can figure out that -9 and -2 are the zeros of this equation. And that's where the y equals 0 when you substitute those 2 x's, -9, -2 in there. And the graph passes the vertical line test. So every x coordinate has at most only 1 y coordinate. So this equation can be written using function notation. We can say it equals f of x instead of x equals y. And so that's a lot of stuff we know about quadratics and the fundamental theorem of algebra. Now, the fundamental theorem of algebra, what that tells us is that a quadratic has two answers, 2 solutions, 2 zeros, even if they're imaginary. Sometimes they're imaginary. So pay attention to where this function crosses the x-axis. These x-intercepts are the number of real solutions when the quadratic equation is set to 0. That's why solutions are called the zeros of a function. So there are 2 zeros to this function, and the degree of the function is 2. X squared. 2 is the largest exponent. Could there be a relationship between the degree of the function and the number of zeros? Let's look at the factorization of the cubic function x to the third minus 12x squared plus 35x. We click on that. They'll factor it right here. First thing they see is you can factor an x out because all the terms had an x. So it's x times x squared minus 12x plus 35. So then we look at that and say, oh, can we factor the quadratics that's left now? And we can. So we can get a -5 and -7 equal to the 35 in the end and -12 in the middle. So the factors of that are x times x minus 5 times x minus 7. And if we set this equal to 0, we can see the 3 zeros or 3 solutions are x equals 0, x equals 5, and x equals 7. So the equation has a degree of 3, and there are 3 solutions. That's not a coincidence. All right, let's look at this video real quick on determining the zeros of this quadratic. And like I say, hopefully this is just very simple review for you because we've done so much factoring with quadratics over our high school years in math that this should come very natural. But let's take a look at how they show this one.
The degree of the polynomial function is 2. So the fundamental theorem of algebra indicates that the function has 2 zeros. The zeros of the function are the values of x, which make the function equal to 0. So, replace the function notation f of x with 0 to begin solving for x. To find the zeros of this function, first verify that x squared minus 3x minus 28 can be factored, using the discriminant b squared minus 4ac. The discriminant is 121, which is a perfect square. So, x squared minus 3x minus 28 can be factored. The 3 terms have no common factor, so factor into 2 binomials. Now, find the factors of the last term, negative 28, that sum to the middle coefficient of negative 3. The factors of 4 and negative 7 satisfy both conditions. So, those are the numbers that fit into the second position of each binomial factor. The zero product property states that for these factors to result in a product of 0, one or both of them must equal 0. Therefore, the zeros of f of x equals x squared minus 3x minus 28 are x equals negative 4 and x equals 7. The x-intercepts of the graph of the function confirm these zeros.
He actually said, oh, there's a second example as well. We'll want to look at that in a moment. He actually said it. He said it out loud at the beginning what the fundamental theorem of algebra tells us. The fundamental theorem of algebra tells us the number of solutions. So I wrote this down to start my notes for the day. The fundamental theorem of algebra and what it actually tells us. The fundamental theorem of algebra says the degree of the polynomial equals the number of zeros or solutions. That's what it all boils down to. If we want to know how many solutions it has, just look at the degree of the polynomial. And let's write some examples down to go with that real quick. So 2x squared minus x plus 4, 2 solutions. 3x to the 5th minus 4x to the 4th plus 2x to the 3rd minus x minus 7 there are 5 solutions or zeros. I like the British spelling of zeros with the E in there. You don't have to put the E in there. Let's do this. 38x to the 11th minus 14x to the 7th minus 2x to the 3rd plus x has 11 solutions. I could just keep writing examples all day, but the degree of the polynomial equals the number of solutions or zeros. What's the degree of the polynomial? The degree of the polynomial is always determined by the largest exponent. And since it's standard procedure to write from the largest exponent to the smallest, it's usually the first term. If they write it out of order, it's still whichever is the largest. 2 solutions, 5 solutions, 11 solutions. Yeah, they're very strong. Yeah, it's that simple. Now, some of those zeros or solutions may be imaginary. There may be duplicate. Maybe it's got a solutions of 2, 2, and 3. It's got 3 solutions, but 2 of them are the same number. But still, there are the same number of solutions as the degree of the polynomial. So he did say that right at the beginning of the video, and I didn't want that to slip by because that's what really we're talking about with the fundamental theorem of algebra. So write that down, put some examples with it like I did there. You can make up your own examples if you want to, as long as you get it right. The largest exponent will be the number of solutions or the number of zeros. Again, remember, they may be duplicate zeros, they may be imaginary zeros, but there are that many of them. All right. Now let's go back and see that second video that they want to show us, because this shows us a good point as well. So this starts out with f of x equals, and look, it's already in factored form. It's in factored form, x plus 2, x plus 2, x minus 1, x minus 3. So they replace it with a 0 instead of the f of x. Set each factor equal to 0. Set x plus 2 equal to 0, x plus 2 equals 0, x minus 1, x minus 3, and solve for x. So we have x equals negative 2, negative 2, 1, and 3. Notice 2 of the solutions are exactly the same. Okay, let it play on. Identify the zeros of the function. Well, those are those 4 solutions we just found. Negative 2, 1, and 3. Oh, let's see what it said there. It was erasing it. Since the value of negative 2 appears twice, it has a multiplicity of 2. A function having 3 zeros are the same would be having a multiplicity of 3. So multiplicity means there's multiple answers, right? A multiplicity of 2, multiplicity of 4 just tells you how many multiple answers there are that are the same. So that's a term that we'll use in math as well, multiplicity. Use the graph to confirm the zeros. So when you graph that, oh, that's an important part. You only see 3 zeros. You only see 3 zeros there. But this bounces off of the x-axis at negative 2. Well, we had 2 solutions at negative 2. So if you have a multiple of 2 or 4 or 6, it will bounce instead of crossing the x-axis. So while we see 3 solutions, there's 4 because that one has 2 solutions that are exactly the same number. All right. So let's play with that thought just a little bit, because we need to kind of get that in our heads to consider. If we graph something, and It's fine to graph it by its factors. That's easier to graph it by its factors. If we have y equals, and we're going to say a factor of x plus 1 times x minus 3, okay, that is a quadratic equation. But I have written it down by its factors. See, there's two x's, so there's two solutions, and there's a solution at -1, and there's a solution at 3. If we add another solution at 3, so we put another x minus 3, now look what happens. It does not cross the x-axis at 3 any longer. It bounces because there are two solutions at the same x. And so when we see a graph, that should tell us something. If I just show you this graph and say, what is the degree of the graph? We figure out how many zeros does it have. Now, it may have some imaginary zeros, so all we know is a minimum. It's a minimum of at least an x to the third. Because we see there's one solution, and we see there's at least two solutions there because it bounced. This could be an x to the 5th. It could be an x to the 7th. It could be an x to the 9th. Because remember, if it has an imaginary solution, imaginary solutions come in pairs. So there would have to be two imaginary solutions if there's one. So this could be a 3rd, 5th, 7th, 9th degree, anything like that. But we know it's not a squared or an x to the 1st because we see at least 3 zeros because they bounce. Oh, excuse me. If I had another solution of x plus 1, so it'd be x minus 1 as the solution, it bounces both places. So that shows us there's at least 4 solutions. It's at least an x to the 4th. And if we multiply these together, we'll have x to the 4th as the largest term because we've got an x times an x times an x times an x. So that's kind of what that is hinting towards. Show more on the fundamental theorem of algebra. What else is it going to tell us here? Determine the zeros of x minus 13, x minus 18, and x plus 9. I love it when it's in factored form because we already can see what the zeros are. The zeros are positive 13, positive 18, and negative 9. Because as you set all those equal to 0 and solve for x, that's what you get, 13, 18, and 9. And when you graph it, we'll see negative 9, 13, and 18. There they are. There's those 3 zeros that we calculated algebraically. X to the 3rd, because x times x times x is going to have 3 solutions. In this case, they're all real solutions. Page 2, the factor theorem. All right, let's look at the factor theorem. You did a great job with the fundamental theorem of algebra because, that's pretty straightforward. We can get that. But not all polynomials will be in factored form. So let's investigate the factor theorem to find polynomials that will factor. All right, so we know what a factor is. Like, 3 is a factor of 12 because you can divide it by 3 and get no remainder. It's a 4. So it was discovered through factoring that binomials x plus 2 and x plus 9 were factors of this function, x squared plus 11x plus 18. We can verify that with synthetic division, which we learned last week, that x plus 2 would divide into there, or x plus 9 would divide into there with no remainder.
Set up the synthetic division problem with the opposite constant of the divisor in the top left corner and the coefficients of the dividend to the right. Underneath the coefficients, skip a line and then draw a line. Bring down the leading coefficient of 1 so that it is underneath the line. Multiply the integer that is below the line by the opposite constant of the divisor. Place the product underneath the next coefficient. Add the vertically aligned integers, and then place the result below the line. Continue this process until all integers have been used. The last integer on the bottom row represents the remainder. The remainder is 0, which confirms the divisor of x plus 2 is a factor of the function f of x equals x squared plus 11x plus 18. Let's try the second factor of x plus 9. Set up the synthetic division problem in the same manner as before. Again, the remainder is 0, which confirms that x plus 9 is a factor of the function f of x equals x squared plus 11x plus 18.
All right, we actually talked about this when we were doing the synthetic division. We just didn't call it a name. We just didn't say it was the remainder theorem. So let me show you. I've written this in my notes. So the remainder theorem tells us when you divide a polynomial by some expression, if the remainder is 0, underline that. If the remainder is 0, then the expression is a factor of the polynomial. Remainder theorem. So when we use that synthetic division and we divided some polynomial by some other expression, x plus 1 or whatever it was, if the remainder was 0, then that expression is a factor of that original polynomial. That's what the remainder theorem tells us. We can check the remainder. If the remainder is not 0, that is not a factor. So that's just a nice little mathematic theorem that we can use to tell factors of polynomials. And they were doing it with a nice simple quadratic, because we're very familiar with quadratic equations. What about the binomial x plus 1? Is it a factor of x squared plus 11x plus 18? Well, if we use synthetic division and set it up, -1 into 1, 11, and 18, and we do all of that, we have a remainder of 8. So since the remainder is 8, not 0, x plus 1 is not a factor of the function x squared plus 11x plus 18. Oh, that's not the remainder theorem. Was that the factor theorem? Which one am I doing? The factor theorem, not the remainder theorem. I wrote down the wrong name. We'll have a remainder theorem in just a moment. I jumped ahead. Yeah, I changed it to factor theorem because we're about to talk about the remainder theorem, which is related and very similar. That's a factor. Is x plus 12 a factor of the function x squared plus 6x minus 72? So go through the steps, set up the synthetic division. Just do the synthetic division problem, and when you get to the end, you find out that the remainder is 0. So yes, x plus 12 is one of the factors, and x minus 6 is the other factors. Remember when we do synthetic division, this is the coefficients of the other term. So more on the factor theorem. Just gives you another example. Is x minus 2 a factor? And they take it and divide it all the way and end up with a remainder of 12. It is not. So, okay. So there's more practice on that. Page 3. This is the remainder theorem. 2 theorems down, 1 more to go. Okay. When a function is in factored form, the zeros of the function, also known as solutions to fx, can be found by setting each factor equal to 0 and solving for the variable. So the fundamental theorem of algebra tells us the number of zeros of the function is equal to the degree of the function. That was our first theorem that we talked about, top of our notes. So the function x squared plus 11x plus 18, we know we'll have 2 solutions. X, when we solve it, factor it and solve it, we get x equals -2 and -9. But since the factors are x plus 2 and x plus 9, the zeros are x equals -2 and -9. If these are applied in synthetic division, the factor theorem told us that we should have a remainder of 0, and it is. So what happens? Oh, this is cool. This is with the remainder theorem. I really like the remainder theorem. This is the remainder theorem. It's easy to give an example for the remainder theorem. Let's do an example to illustrate what it says. All right, remainder theorem. If we have, and let's just set up a division problem over here. We're dividing, I'm just going to make one up, x squared minus 7x plus 14, and we're dividing it by x minus 2. Right, so we're going to set that up as synthetic division. 2, we have a number out here, 1, negative 7, and 14. So what it wants to know is this a factor of that? So I can do the synthetic division and use the factor theorem to figure that out. But let me show you this. I can use the remainder theorem this way. I'm writing it in function notation, same thing. And x minus 2 means we're using 2. So if I just put 2 in, f of 2, so this would be 2 squared minus 7 times 2 plus 14. 2 squared is 4. That is negative 14. That is plus 14. Four minus 14 plus 14 equals 4. The remainder theorem says if I divide this, this is the remainder. Not a factor. X minus 2. I know it's not a factor. This tells me the remainder. If I just substitute that 2 in, let's do this to verify this was right. 1 comes down. 2 times 1. Oh, this come up with something different. Wait a minute. Did I do that right? Oh, no, wait. Add these together. No, I'm doing it right. Negative 7 plus 2 is negative 5. 2 times negative 5 is negative 10. Oh, look. There's our remainder. The remainder theorem gives us the remainder. If we just substitute that 2 in, so x minus 2, we'd have to solve, x minus 2 equals 0, add 2. So I'm checking the solution of x equals 2. So if I just substitute it in, this will tell me what the remainder is. So then I can use the factor theorem to say, is the remainder 0 to know it's a factor? It is not 0. I think the remainder theorem is pretty cool. Substitute it in, it gives you exact same information. The only thing it doesn't give us is it doesn't tell us what the other, what the quotient is. But it does give us a shortcut to know what is the remainder. Is this a factor? So, however, if you want to write that up in some way to understand it, I think this one works best by giving an example, because it does not have a remainder of 0. But it's a shortcut to tell you what the synthetic division will tell you. Again, that's only going to work with a binomial that's an x. It doesn't work if I'm dividing it by, 3x plus 7 or something, or x squared minus 1. It's not going to work. It only works in the same problems that synthetic division does. When a 0 of the function is substituted in the function, the result is 0. This makes sense. So on theirs, they're checking one of the solutions they know. So they know that the solution is x minus 2 and x equals negative 2 and negative 9. So when they substitute negative 9 in there, they get a 0, which we would expect. The remainder should be 0 if that is a factor. So if they divide it by x plus 1, which is not a factor, use that negative 1, you get the remainder of 8 with the synthetic division and with the remainder theorem. Here it is in words, if you want words in your notes. When the opposite of the constant term of the binomial, which means if it's x plus 1, you got to substitute negative 1, right? is substituted for x in the function, the result is equal to the remainder when the function is divided by the binomial. This is the remainder theorem. It helps you determine whether or not the number is a zero of the function. So if you think something's a zero, substitute it in and see if the remainder is zero. So the remainder theorem delivers some important facts. Given a polynomial function and a number, a, say, is 3 one of the zeros, well, then x minus 3 would be a factor if it is. So you can use long division to check it out. You can use synthetic division. You can use factoring methods. So it is a zero if the graph passes the x-axis at that number, or substituting a into x minus a will equal 0, or substituting a will result in f of a equals 0. The remainder theorem will give you the remainder. So example, find the remainder. All right, let's do that as a practice problem on the back. Okay, so it wants to know what is the remainder when we divide this by this. So we got a few ways to do that. You can do long division. You can do synthetic division, or now that we know about the remainder theorem, I can take negative 10, since that's x plus 10, and substitute it in. Negative 10. 5 times negative 10 squared plus 51 times negative 10 plus 16. Negative 10 squared is 100 times 5 is 500. 51 times negative 10 is negative 510 plus 16. 500 minus 510 is negative 10 plus 16. So the remainder is 6. This is not a factor of this. The remainder is 6. So they did it with synthetic division, ended up with a 6. They did it by substituting it in, like I did, and you get a 6. So it's kind of like a shortcut for synthetic division. I don't know. It gives you the same thing. So if you like that better than synthetic division, you could do that. The remainder is the same way. So there's another example in there you can click on and look at. Find the remainder when you divide that by x plus 8. And that's a big, long, 4th degree polynomial. But let's look at the lesson summary so we can jump to the next lesson. What key features of a polynomial can be found using the fundamental theorem of algebra and the factor theorem? And what does the remainder theorem allow? How does that allow it to be identified? So a theorem is a proven statement based on experimentation. So we talked about the fundamental theorem of algebra. It says the degree of the polynomial is equivalent to the number of zeros, both real and complex, which means real and imaginary. Real and imaginary. The factor theorem says that if the remainder is 0, then the term is a factor. And the remainder is 0, x minus 5 is a factor. And the remainder theorem says when the opposite of the constant from the binomial divisor is substituted into a function for x, the result is the remainder. So what it all means, given a polynomial function and a number a, if x minus a is a factor, then the a is a 0. And we can prove it in those different ways. So there is a couple of pages of practice problems that you can try. Find the zeros and drag them to the pro location. Negative 2 is a 0 of one of these. Now here's the nice thing. These two are in factored form. So I can look at that and tell you the 3 zeros, right? X plus 2, and x minus 9. Let's go over that real quick in case anyone struggles with that concept. What are the zeros of this equation? Because you should be able to look at that quickly and know what the zeros are, the solutions, the zeros. I'll spell it with just no E this time. Zeros. 0, negative 2, and 9. Because it's in factored form. It's already factored out. To find the zeros of a polynomial when it's factored, you take the whole thing and you set it to, that's a minus. You set it equal to 0, and you say, okay, to find the 3 zeros, you set each term equal to 0. And solve for x. Well, this one's already solved for x. That's the first one. Subtract 2 from each side. X equals -2. That's the second one. And add 9. X equals 9. That's the third one. So when they give you it in factored form, what would it take to make this 0? -2 plus 2 would be 0. 9 minus 9 would be 0. That's the zeros or solutions. And we know there should be 3 because this is an x times an x times an x. This is going to be an x to the third function. We multiply those together. You'll get an x to the third. So, all right. Factored form is real easy to get the zeros. So we know -2 is one of the zeros of that because it has x plus 2 right there. And this has x minus 1, x minus 5, and x plus 12. So we know -7 is not a factor of that. And it's not a factor of that. It's got to be this one, just by process of elimination. Because we know this one's 0, -2, and 9. This one is 1 and 5 and -12. It's all right there. So if it's not one of those, it's got to be over there. All right. Is x plus 3 a factor of this function? You got a couple of ways to figure that out now, right? Synthetic division. You have the remainder theorem. However you want to do that. There's 3 problems. The other page of practice problems. According to the fundamental theorem of algebra, how many zeros does this function have? That should be quick and easy. What's the largest exponent? Oh, this has 5 solutions. That's 5 zeros. Some of them may be imaginary, but there's 5 because it's x to the 5th. Great, correct answer. So it'll give you some more practice problems there. What are the zeros? Factor that. Set it equal to 0. All right, activity 2. Is this a factor of this? So, all right, let's go look at the assignment that goes with this first lesson. According to the fundamental theorem of algebra, how many zeros does this function have? 3x to the 4th plus x plus 2. Oh, come on. You got that one quickly, right? Which of the following is a 0? So you can check all of those. Oh, well, this is in factored form. X plus 3, x minus 7, x plus 5. That should make that pretty quick. Is x plus 10 a factor? Use one of your methods to figure that out. Find the remainder when this is divided by x minus 5. Use the remainder theorem. Put a 5 in for x. See what the remainder is. Find the remainder when this is divided by x minus 3. Put a 3 in. 5 problems. All right, that's not bad. Let's look at the rational root theorem. Oh, wait a minute. It makes me finish this last one before I can look at that. All right. I'll go back here and turn this in. I answered the question. I'll come back and redo it. The rational root theorem and Descartes' rule of signs. This is so cool. All right, when making a new car purchase, buyers search for a make and model within their price range. Then they'll visit their local dealership and they'll take a test drive. So if you're looking to purchase a dog or cat for your home, you choose a breed, you'll go to the animal shelter or pet store or breeder, play with the animals, find the one you like. If you're going to buy an apartment or a house, you decide on location, a price range, arrange for a walkthrough. So in each of these situations, you begin with this wide variety of possibilities. Then you narrow it down based on the price, based on the location, based on what other preferences you have. And then after you test the possibilities, you make a decision. Well, a similar process is used to find the solutions of a polynomial function. So after this lesson, we're going to learn what does the rational root theorem and Descartes' rule of signs indicate about the zeros of a polynomial function, and how can the zeros in end behavior allow a graph to be sketched. So let's look at this. F of x equals x to the 5th plus 2x to the 4th minus 4x to the 3rd minus 4x squared minus 5x minus 6. So the fundamental theorem of algebra says the degree of this function is equal to the number of zeros. Well, the degree is 5. So there are 5 values of x that will make this function equal to 0. There's 5 zeros. You have any idea what they might be? Well, the remainder theorem says you can find a possible 0 using synthetic division or substituting the number in. If the tested number creates a remainder of 0, then that will be one of the zeros of the function. So we can find all 5 of them. So to find whether 1 is a 0 of this function, we can set up a synthetic division problem. Say, okay, is 1 a solution for x to the 5th, 2x to the 4th, etc.? So first step, bring the 1 down, multiply 1 times 1, add to the 2. Multiply 1 times 3, add to the negative 4. Multiply 1 times negative 1, add to the negative 4. Multiply 1 times negative 5, add to the negative 5. And then multiply, add to the negative 6. We get a remainder of negative 16. 1 is not one of the zeros because the remainder is not 0. 1 is not a root, not a 0, not a solution. So it would be very time consuming to say, okay, well, I know there's 5 solutions. It's not 1. Let me try 2. Now let me try 3. Now let me try 4. Oh, let me try negative 1. Let me try negative 2. That would take a long time. It would be very time consuming to test every real number to find the 5 solutions. But there is a better way to do it. And this is where the rational root theorem becomes very important. So if we factor this quadratic function, 6x squared plus 9x minus 7, it will factor to be 3x minus 1 and 2x plus 7. Okay, so they've done all of that, set it equal to 0, which means the solutions are x equals 1/3 and x equals negative 7/2. We wouldn't even have tested that. We've been testing 1, 2, 3, negative 1, negative 2, negative 3. So those are fractional answers and zeros, which is very possible. A lot of times when you graph things, that is where it crosses the x-axis, at not exactly at a 0 or at an integer. So the rational root theorem states that a list of potential rational zeros of a polynomial function is found by listing the factors of the constant term, defined as p, and dividing those by the factors of the coefficient, defined as q. So here's what we're going to do. We're going to get a piece of paper, and we're going to play with this, and we're going to find the factors, the possible factors of this really long, nasty polynomial. This is going to be minding our P's and Q's here. We have this polynomial, and we want to find out what are the zeros. And we know there's 5 of them, 5 zeros for this equation, which means we would need to factor this and all kinds of stuff to figure out what the 5 factors are and set those equal to 0. And you're like, my goodness, Mr. Brock, can we go back to quadratics? Well, this is how it works. We're going to find P divided by Q. And you're like, whoa, what's P's and Q's? P would be the constant on the end. Okay. This is going to be P. Q is the coefficient of the x. Well, there's no coefficient. Well, there is, right? There's a 1. We just don't write it. There's coefficient of 1. So the possible factors that we need to test are the factors of negative 6 and divided by the factors of Q. Okay, so the factors of negative 6 could be 1 and 6 and negative 1, negative 6, 2, 3, negative 2, negative 3. We know there always could be positive and negative. Well, I'm sorry, for a negative, one of these would be positive, right? And then 1 is just 1 and negative 1. So if we look at all the possible P's over Q's, Since this is going to be 1, it's just 1 over 1. So it's possibly 1 over 1, which is just 1. Everything's over 1, so it's just these numbers. It could be plus or minus 2, because it could be the 1. Could be a plus or minus 3. Could be a plus or minus 6. And so when we look at this, what are we calling this? This is the rational root theorem. The rational root theorem. By finding all the p's and the q's, this tells us the rational root theorem. Rational root theorem says if there are any rational roots, there could be some imaginary roots and other stuff, has to be one of these. Oh, not that. Rational root says the possible roots or zeros, because it's called the same thing, a root or zero, has to be one of these. I find the factors of this, put it on the bottom, but on this case, it was just divided by 1. Right, so we didn't really write the over 1. The p's go on top. All the possible numbers that could fit into p go on top of the fraction. All the possible q's go on bottom, but there's just 1 or negative 1. So plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. That narrows it down. If we're trying to find the roots of this, instead of testing every possible number out there, it's got to be one of these 8 numbers, which means we can start testing that with synthetic division. This is 1, 2, negative 4, negative 4, negative 5, negative 6. And we can divide. Let's see, they tested 1 already, did they not? Yes, they tested 1. 1 did not work. It had a remainder. So 1 is not 1. And let's try negative 1. 1 is out. So we know it's 1, negative 1, 2, negative 2, 3, negative 3, or 6, negative 6. And 1 did not work because they tested that. So we're testing negative 1. Bring this down. 1. Negative 1 times 1 is negative 1. Add those together, it's 1. Multiply that together, it's negative 1. Add those together, it's that. That is a positive 5. So that adds up to 1. That multiplies to negative 1. We add those, we got negative 6. Negative 1 times negative 6 is a positive 6. Okay, negative 1 is a solution. That is one of the rational solutions. Let's check 2. 1, 2, negative 4, negative 4, negative 5, negative 6. Bring that down. 1. 1 times 2 is 2. 2 plus 2 is 4. 8. 2 times 4 is 8. Add those together. 2 times 4 is 8. Add those together. 2 times 4 is 8. Add those together. 2 times 3 is 6. Oh, that one works as well. So 2 is also one of the solutions. 3 solutions left because we know there's 5 total. If they're all rational. If they're rational. If there's not imaginary solutions. But we could go through all of those, and I'm going to look in the lesson because they did all those for us. We could continue on. But we're going to kind of go off of their work. So here's where they tested it. You know, they tested 1 and had that remainder. We saw that. But negative 1 worked. So that was one of our solutions. Then we tested 2. 2 worked. If we test negative 2, it will not work. has a remainder of 20. So far we know solutions are -1 and 2. You check 3. Oh, very large remainder. How about -3? -3 works. 6, huge remainder, and a very large negative. So what we found was there's a solution of -1, a solution of 2, and a solution of -3. But it has to have 5 zeros. What happened to the other 2 zeros? So think about that for a while we practice finding P's and Q's values. All right, I'll give you a spoiler hit, right? Spoiler. The other 2 are imaginary zeros or irrational. All right, find all the possible rational zeros of this. Let's practice another one because we need practice with that. So, and we want to find the possible rational zeros. So the P over Q. So the possible factors of 12, and we don't have to worry about the negative because we're going to take the plus or minus of every one of them. So for 12 would be 1 and 12, 2 and 6, 3 and 4, right? Because all of those numbers would multiply together to be 12. So 1, 2, 3, 4, 6, and 12. So that's the P. For Q, this time we have a 2. So that's just 1 and 2. So here's how we list all of them. We got to take all the P's and put them over all the Q's. So the first one, let's just do the ones, which means this will be plus or minus 1, plus or minus 2. We'll just list all of these because putting them over 1 won't change anything. Could be plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. Now we got to go through all of them again using the 2. If the Q is 2, so this are the P's, these are the Q's. Also, it could be 1 over 2, could be plus or minus 1/2. Could be 2 over 2. Now 2 over 2 is just 1, so we don't have to write that one again. That's the same thing. 2 divided by 2 is just 1. So that one's not there. But 3 divided by 2, so it could be plus or minus 3/2. And I'm going to move down on another line here. 4 over 2, that's just equal to 2. We've already got that one. 4 over 2 is the same thing as 2. 6 over 2, well, that's the same thing as 3. We may not need any more of these. And 12 over 2 is the same thing as 6. Okay, so that's the end of the list. So it could be 1, 2, 3, 4, 5, 6, 7, 8, 16. There's 16 possible zeros, including some fractions. Plus or minus 1, 2, 3, 4, 6, 12, 1/2 or 3/2. Now, they didn't ask us to find it. They just said find all the possibles. So if we look at what they did, first find the factors of P, which are, 1, 2, 3, 4, 6, and 12, which we did. Find the factors of Q, which are just plus or minus 1, plus or minus 2. Now you list all of them. Now they went ahead and listed them with the 1 over 1, 2 over 1, 1 over 2, 2 over 2, 3 over 2, 4 over 2, 6 over 2, 12 over 2. But when you simplify that, some of those are duplicates. So the final possible rational zeros are plus or minus 1, 2, 3, 4, 6, 12, 1/2, and 3/2. So that's all they ask us to do. Just find the possible. We don't have to start doing synthetic division. We don't have to find the zeros. Just find the possible ones. And here's more on the rational root theorem. More practice problems. This uses 8 and 1. So the Q is 1 this time. So the possibles are plus or minus 1, 2, 4, and 8. Here's one that has a 3 and a -11. So you would go through and find all of the ones and put those in there and see if you got it. Okay. So let's go on because okay, we narrowed it down to what was it, 16 choices on there? We can do better. There's another shortcut we can use. Descartes was a French mathematician that figured out a lot of really good stuff, and this is one of them. So it was determined by the fundamental theorem of algebra, the 5 values of x that make this original equation equal to 0. We found 2, -1, and -3. Here's the graph of that x to the 5th one that we were using. And there's the 3 we found, 2, -1, and -3. And we said, where's the other 2 solutions? Well, it turns out they're imaginary, right? They're imaginary. The other 2 zeros. Think about the rational root theorem. The term rational describes numbers that can be written as fractions. That means irrational numbers and complex numbers, which is imaginary, cannot be found with this theorem. Complex zeros can only be found using the quadratic formula or completing the square. So Descartes was a 17th century philosopher whose development of the coordinate plane, he invented the XY graph and the geometric relationship of algebra equations, had a major impact on math. So here's what he figured out. If we take this, let me write this equation down once again, because we're going to talk about Descartes' rule of signs. Okay. This is really cool. Let's see. Let's use this one actually instead of the example they gave us. Let's use this one. So this says Descartes' rule of signs. Writing down this equation right here that they want us to use, that we were using. Let's check to see what the signs are here. So this is a positive, right? And this is a negative. This is a positive. This is a negative. When we go from one term to the next, how many times does the sign change? This change from positive to negative. This change back from negative to a positive. This change from positive to a negative. 3 sign changes. Three sign changes. So that means 3 positive roots. Possibly. So of these 18, if we start doing synthetic division and we find that, yep, this one works, this one works, this one works. If I find 1, 3, and 4 all work, I don't have to test 6 and 12 and 1/2 and 3/2, at least not the positive one, because Descartes' rule of signs says at most there are 3 positive roots. Like, oh, well, that's pretty darn cool. Can we tell how many negative roots there are? We can. If we substitute negative x, so we've got 2 times negative x to the 4th minus 10 times negative x squared plus 5 times negative x minus 12. Let's go through here. Simplify this. What's negative x to the 4th? Negative x times negative x times negative x times negative x. So that's a negative times a negative, which is a positive, times another negative times a negative, which is a positive. So this will be the same as 2x to the 4th as a positive. Negative x squared. Negative x times negative x is a positive, times a negative 10, so that's going to be negative 10x squared. 5 times negative x, it's positive times a negative, so that's going to be negative 5x and minus 12. Okay, how many times does the sign change? This is positive, this is negative. There's 1, no, 1 sign change. 1 negative root. Guaranteed one negative root. You're like, wait a minute, you said there was 3 possible positive roots, but you're saying one guaranteed negative root? If we start testing -1, -2, -3, and maybe a -2 worked, we don't have to test anything else because there's only going to be one negative root. Okay, Mr. Brock, you sound so positive on this. Because of this. Roots. Positive. Negative, just naming the kind of roots. Say kinds of roots or zeros or solutions, whatever you want to call them. They all have the same name. It could be positive roots. There could be negative roots. There could be imaginary, also called complex. But here's the secret. Imaginary or complex roots, capitalize this, always come in pairs. I'm going to highlight always. I'm going to underline it in red. And I've capitalized it. If there's an imaginary solution, there's always 2 imaginary solutions. Always. Combine conjugates, conjugate pairs. So, looking at this problem, this only tells us what's possible. Because it doesn't know, DeCartes' rule doesn't know if any of these are imaginary. But here's what we do know. For this problem, positive, negative, complex. If we're breaking it out into what's the possibilities, we know there's 5 solutions. We know there's 5 solutions. And it could be that 3 of them are positive, 1 is negative. Wait a minute. There's not. This has 4 solutions. I'm wrong. Like dx. Wait. There was not 5 solutions. I was thinking of the original problem that they were working. Ours has 4 solutions. So if 3 of them are positive and 1's negative, that means there are no imaginary solutions. But there's another possibility. It could be that we have 2 imaginary solutions and only 1 positive, which means there's still 1 negative. There are no other possibilities. Because with 1 negative, we know the negative is not imaginary. Because there would have to be 2. Because they're always in pairs. So if there's 1, there's guaranteed 1. If there's 3, well, maybe there's 3. Maybe there's only 1 because maybe 2 of them are imaginary. Because if it's imaginary, there's going to be 2 of them, not 1. But now we know when we start searching to figure out which of these solutions, once we hit a negative one, we're done. We're not checking the other negative ones. And if we hit 3 positive ones, we can stop there. Now, if we find a positive one, we don't find another one, don't find another, and we check here, and this is not a solution, we don't have to check the last one because there's not going to be 2. DeCartes' rule of signs. 3 sign changes, 3 possible roots. 1 sign change. Once you substitute negative x in and simplify, you got to simplify it. Descartes helps us figure out and eliminate where we don't have to check 16 times with synthetic division. Narrows it down. Find the possible real zeros. They're using an x to the 5th equation. So it had 1 sign change. It went positive, positive, negative, 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 1 sign change. So there's only 1 possible positive real zero. and we found it to be 2. Then you substitute negative x in and check it again. Simplify it, and find out how many sign changes then. Negative to a positive, positive, positive to a negative, back to positive, back to negative. Oh, look, there was several. There's 4 sign changes. So there could be 4 negative zeros. So the number of sign changes was 4. So it could be 4 negative zeros. It could be 2 negative zeros and 2 complex, or maybe there's 0. Here's the possibilities. There's 1 positive. So we know there's 1 positive guaranteed. Negative on this one that they checked, there was 4 possible negative solutions, or maybe there's only 2 and 2 of them are imaginary, or maybe there's none and there's 4 imaginary. So anytime the number is 2 or larger, you got to consider another possibility that there could be 2 imaginary instead. All right, let's look at the next page of this. See if it gives us any more information. All right. Good. We got 2 videos and then a problem for us to do. Let's look at these 2 videos real quick. We got a little time left. All right, the possible number of positive zeros for this equation right up here.
The first step is to determine the possible number of positive real zeros. To do this, count the number of sign changes in the function as you move from left to right. If positive terms are green and negative terms are red, notice that the sign changes 2 times. There are 2 sign changes. So it is possible there are 2 positive real zeros. Descartes' rule of signs states you must also subtract 2 from the number of sign changes, as long as the difference is not negative. So, it is also possible that this function has 0 positive real zeros. Next, find the possible number of negative real zeros. Use f of x. To find f of negative x, substitute negative x for x. Then simplify. Notice that only the terms with odd-numbered exponents experience a sign change. Identify positive and negative terms. And count the number of sign changes as you move from left to right. There is 1 sign change. So, this function has 1 negative 0. Can you subtract 2 from 1 without getting a negative number? No. So, 1 is the only possibility. Finally, find the possible number of complex zeros. The fundamental theorem of algebra states the degree of the polynomial is equivalent to the number of zeros in a given function. The degree of the function is 3, so there must be a total of 3 zeros. The combination of positive real, negative real, and complex zeros must total the number of zeros in that function. You have already discovered that there are 2 or 0 positive real zeros and 1 negative real zero, so consider all combinations. If there are 2 positive real zeros and 1 negative real zero, there cannot be any complex zeros. Another possibility is that there are 0 positive real zeros and 1 negative real zero. In this case, the remaining 2 zeros must be complex. As you can see, the function f of x equals 2x cubed plus 11x squared minus 9x plus 1 has 2 or 0 positive real zeros, 1 negative real zero, and 2 or 0 complex zeros.
All right, so I just want to point out this was an x to the third degree, and they did a great job of explaining positive, negative, and complex zeros. She's going to work on a fourth degree. So we expect there to be 4 possible zeros, but how many are positive, how many are negative, etc.
Hello, today we're going to look at the rational root theorem and Descartes' rule. Here we have our polynomial function, and we're going to find our possible roots first. We're going to look at p, which is the constant, and we're going to look at q, which is the leading coefficient. We're going to list all the factors of 9, which in this case is positive or negative 1, positive or negative 3, and positive or negative 9. And we're going to list all the factors of 2, which in this case is positive or negative 1, and positive or negative 2. Then we're going to go ahead and divide p by q, which means I'm going to take each one of these factors and divide them by each one of these factors. So the first one is going to be positive or negative 1 divided by 1. Then we have positive or negative 3 divided by the 1. And positive or negative 9 divided by 1 as well. Now we're going to do the same thing but with the 2. So I got positive or negative 1 over 2, positive or negative 3 over 2, and then positive or negative 9 over 2. Our next step would be to use synthetic division to figure out which one are our roots. But before we do synthetic division, we're going to go ahead and use Descartes' rule to figure out our possible roots. So if I have 2x to the fourth plus x to the third minus 19x squared minus the 9x plus 9, I'm going to see how many times the sign changes. Well, the first one doesn't change. The second one, there is a change. Then we have no change, and then we have another change. This means that I have 2 or 0 possible positive roots. Now I'm going to repeat the process, but this time I'm going to plug in a negative x. So this is going to be 2 times negative x to the fourth power plus a negative x to the third power minus a 19 negative x to the second power minus a 9 times a negative x plus 9. If I simplify this, I'm going to get 2x to the fourth minus x to the third minus 19x squared plus 9x plus 9. So now I'm going to go ahead and see the sign changes. I have one sign change here, no sign change here. I have another one here, and none there. That means I have 2 or 0 negative. So to determine the complex roots, I'm going to go ahead and make myself a chart. And what I'm going to do is I'm going to determine how many possibilities I have between my positive and negatives, which means I can have either 2 positive with 2 negative or 2 positive with 0. So you got to match each one. So we got 2 positive with 2 negative or 2 positive with 0. And then we'll repeat the process. With 0, we got 0 positive and 2 negative, 0 positive and 0 negative. So to find the complex roots, we go back to the degree of our polynomial, which is 4, and we have to make sure that we add them across and they equal 4. So 2 plus 2 is 4. That means there's a 0 complex. 2 plus 0 is 2, which means I have 2 complex. 0 plus 2 is 2, so I have 2 complex. And 0 plus 0 is 0, so that means I have 4 complex. Now I'm going to go ahead and use my synthetic division to see if I can find one of my roots. So I'm going to go ahead and start off with the negative 1. So I have my coefficients, which are 2, 1, negative 19, negative 9, and 9. And I'm going to go ahead and start off by bringing my 2 down. 2 times negative 1 is going to be negative 2. So 1 plus negative 2 is going to be negative 1. Negative 1 times negative 1 is going to be a positive 1. And negative 19 plus 1 is going to be negative 18. Negative 18 times negative 1 is going to be a positive 18. And then negative 9 plus 18 is going to be 9. And then 9 times negative 1 is going to be negative 9. And 9 plus negative 9 is 0. Which is good news because that means that negative 1 is one of our roots. So this is where we can use Descartes. Because when we did Descartes, it said that we could either have 2 or 0 negative possible roots. Well, if we have 1, that means we have to have one other one, which means that we can get rid of the 0 because that's not one of the possibilities. And then you can go through and go ahead and use any one of your other possible roots with synthetic division to find the remaining roots. And that's how we use the rational root theorem.
All right, that's a good start on that problem. She walked through step by step by step, showing you all of that, starting with the P's and the Q's and figuring out how many possible there are in both situations. There's 2 or 0 with positive and negative, which really varies in your complex. But she found one of the roots already that was a negative. So we don't know, once you find the second one, you can stop testing the negative numbers because there's not going to be more than 2. Here's another example. Determine the possible positive, negative, or complex. So you go through the same step. No change. There's one change. No change. There's a change. So there's 3 sign changes. Just looking at the original problem. So that means there's possibly 3 or 1 positive roots. Right? So it could be 1 if 2 of them are imaginary. So 3 or 1. Negative, you have to substitute that negative x in there, which means that'll change, that'll change, that'll change. So you'd have, let's see, that'd be a positive to a negative to a negative to positive. So it looks like 2 sign changes. Is that right? I'm not 25. 2. Yeah, there's 2. Positive, negative to positive, and everything else stays positive the rest of the way out. So it could be 2 or 0, which means select what's the possible number of complex zeros. How many total zeros are in the function? There's 4. Oh, I'm sorry, 5. This was the 5th degree. I was looking at the wrong problem. 5th degree, yep. 5 zeros. And all combinations down here. If there's 5 zeros, you could either have 3 positive and 2 negative and no complex, 1 positive, 2 negative, 2 complex, 3 0 2 or 1 0 4. There's 4 possibilities. So here's another example on Descartes. Find the possible. So there's several examples here you can work through. What's on page 4? Creating sketches of a graph from the zeros. Okay, if you know the zeros, if there's 2 of them, it bounces. Otherwise, it's going to cross at those in there. So find the y-intercept. Oh, that's a good one. Y-intercept, if you're sketching a graph, like if we look at this, we know what's the y-intercept. Well, we can quickly tell the y-intercept because anything that has a 0, the y-intercept is when x equals 0. So if x equals 0, that goes away, that goes away, that goes away. Negative 12. Whatever the number is at the end, this is always the y-intercept. In any equation, the term that does not have an x is the y-intercept. X to the 5th plus 2x to the 4th, x to the 3rd, x to the 3rd. Negative 6 is the y-intercept. Negative 12 is the y-intercept. All you have to do is look to see, I don't have any other equations over there. 16 is the y-intercept. So all you have to do is look to see that. And then if you have the factors, we know what the zeros are. So negative 4 is the y-intercept because it's the number on the end. Then once you find the zeros, you can plot those, plot the y-intercept, plot the zeros. Like this, found 3 zeros. And then do a rough sketch. If it's a 3rd degree that's positive, it's going to go up to the right, down to the bottom. And you can use Desmos to look at that. But let's look at the lesson summary because we're out of time. Rational root theorem helps you find all the possible rational zeros. Find the factors of P, find the factors of Q, put every P over every Q. And this one only has 8 choices: positive or negative 1, positive or negative 11, positive or negative 1/3, positive or negative 11/3. Descartes will help you rule out several of those because you know there can only be so many positive and so many negatives. And then you're left with the rest are complex if there's 2 or more of imaginary zeros. So 3, 2, or 0, or 1, 2, or 2, or 3, 0, or 2, or 1, 0, and 4. Just remember, there's always pairs. Complex always pairs. They do have some practice problems for you on page 5. So I recommend, since this is something new and different and kind of crazy, you should do some practice problems. Find the possible rational roots, and they give you 4 choices. P over Q, P over Q. 2 problems there once you choose the first one. Activity 2. Use DeCartes rule of signs to analyze the zeros. How many possible positive, negative, and complex? And you can check your answer. And there's 3 problems right there. Activity 3. Sketch the graph of that. That's a good one to practice sketching the graph. You know the y-intercept. You can find the roots by using Descartes' rule, the rational root theorem, Descartes' rule, and synthetic division to find what the roots are, and then you can sketch a graph of it. So it's good practice to do that before you graph it, to do those things. And they got all kinds of good stuff there. So let's look at the assignment real quick. So we're about to be out of time. What are the possible zeros? The possible rational zeros using the rational root theorem. What are the possible rational zeros of this? What are the possible numbers of real, negative, or complex zeros? Positive real, negative real, and complex. There's 3, 4 different choices for this equation. Another one, possible, positive, negative, complex. And which of the graphs represent this? You may be able to tell a lot just by looking at the y-intercept. All right, these lessons that we've looked at is really putting everything together to where we can look at these crazy huge polynomials, 3x to the 5th minus 7x, and we can tell a lot about them in a relatively short amount of time. And this takes longer than a lot of the other problems we've done. But, you know, with our factor theorem and remainder theorem, with synthetic division, with the rational root theorem, Descartes' rule of signs, we can immediately start ruling out a lot of numbers where it's like, well, I don't even need to check to see if 2 is a root because the rational root theorem didn't even list that as a possibility. When I looked at all the factors of P and Q, 2 wasn't even one of them. You know, could be something along that lines. Descartes helps you even rule out even more. Okay, oh man, I found out there's like 16 possibilities, 8 positive and 8 negative. And then I do Descartes' rule of sign to find out, oh, there are no negatives. There's no possible negatives. So I can rule out 8 of them. I don't even have to do synthetic division on any of the negative ones. If Descartes' rule of sign says there are no negative solutions, there's only positive or complex. Great. Save me a lot of work. I don't even have to check 8 of them. So between this, we may start out with 16 or 18 choices of possible roots, but we started with an infinite amount when we first looked at it. It's like, I have no idea. I can rule it down to a finite number of possible rational roots. And then Descartes helps us whittle it down even farther. Once we find 1 or 2 or 3, it's like, oh, well, there can't be any more because Descartes' rule says there's only 3 positive possible roots. And I found 3 possible roots. So I'll just scratch the rest of them off and no need to even check them. That's just wasting my time. So all of this together is a pretty powerful tool belt you have for math now to be able to learn things about all of our rational roots and stuff. I will take pictures of what I did here and put it in our Google Classroom page, just so we've got a little bit of help with all the fundamental theorem of algebra, the factor theorem, the remainder theorem, Descartes' rule of signs, rational root theorem. We really got into some good college math today and a lot of higher math thinking, being able to not just plug things into a formula and solve the quadratic formula or something. No, really looking at these large polynomials, these high degree polynomials, and really doing some good math with it, really figuring out some things. So I'll get this video edited as quick as I can. I will post these notes on there so you can look at them. But we looked at 5 theorems that have been proven in mathematics, and figured out how to use them to really help us take a huge problem, factoring the x to the fifth. My goodness, factoring an x to the fifth equation. But we could do that in probably 5 to 10 minutes most of the time and get the 5 factors. And that'd be pretty cool. Unless they're complex. We didn't really mess with how would we find the complex ones. But we can use the remainder theorem and factor theorem and all that and find the zeros. So we could have the factors right there. So, all right, guys, this is a B-Day Friday. So if you get started on this, and I would recommend getting started on this before Thursday and Friday's class, because you may want to come to class Thursday and Friday and say, okay, I thought I had this, Mr. Brock, but wow, can you give me a hand with this? I'm kind of stuck on problem number 1. You bet. We'll pull up problem number 1 and work on that together and get you back on track if you kind of lose your way. So, all right, guys, have a great week. If I see you Thursday or Friday, great. If not, I'll catch you next week. Have a great time. We'll see you later.